4.6, linear relations and slope. So the goal here is to learn how to understand how constant rate of change and its connection to linear relations. So we've already looked at things that, the rates of change and how this steepness affect the line. So in our everyday lives, there are many examples where we measure how steep something is. So in designing a ramp, for example, a roof, a road, stairs, okay, you always have to consider the incline, the steepness. Many different words for it. So we have slope, gradient, the angle, the incline, or the slant. Okay, this idea of measuring slope is just very, very key when studying linear relations. Okay, so whenever you hear these words, steepness, slope, rate of change, these are all equivalent. Okay, they're used to express the same thing. So now you may remember how we calculated this steepness, this slope. It's always a measure of rise, how far you rise, or over the run, how far you go on the horizontal. Okay, so if I was interested in calculating these slopes here, remember these are all different steepnesses. Okay, I would just say slope is equal to the rise over the run. So how far do you go up or down vertically is the rise. How far you go left or right horizontally is the run. Okay, and so it's up for positive, right for positive. So here the rise is 60, and the run is 70, and that's my slope, 60 over 70, which is equivalent to 6 over 7 in lowest terms. For this one, slope is 60 over 110. And that is, in lowest terms, 6 over 11. And for this one, slope is 80 over 100, or in lowest terms, 4 over 5. 8 over 10, which is 4 over 5. Okay, so it's always dividing this rise by your run. And here's that formula summarized. Slope equals rise over run. And on the Cartesian grid, if you're given a line segment AB, or a line, any 2 points on a line, your rise is the change in your y values, from going from a y value of 1 all the way to a y value of 4, divided by your change in your x values, which would be a 3 and 1. So it's a distance of 2. So my run is 2. My rise is 4 minus 1, which is 3. So it's 3 squares going up, 2 squares going to the right. Okay. So that would be a positive slope, right? So positive slope looks like that on a graph. It's an upward trend. What about this other graph here? What if my rise is going down? So if your rise is going down, it's going down two grid squares or 2 units, and it's going to the right 3 units. So my rise is negative instead of positive. So that would result in a negative slope on my graph. Downward trend. So determine the slope of the given lines. Well, if you have 2 points here, let's create a triangle. So here's the triangle we're going to create, and we can use this triangle to measure the rise and the run. So what's the rise? Well, each grid square represents 1 unit. So 1, 2, 3, 4 squares represents my rise. So here, rise is equal to 4. And what about the run? Well, I have 1, 2, 3 squares along this edge of my triangle. So this part here is my run. 3 is equal to the run. So my slope is my rise over run, which is 4 over 3. What about on this triangle? What if you're only given 1 point? Well, pick another point on the line that you can easily read. And I believe I can easily read this point down here as 5 and negative 2. Okay, so if I'm interested in calculating my slope, let's draw another triangle from 1 point to the other point. All right, and there you go. And let's measure, so each square is representing 1 unit. So if I count the squares, 1, 2, 3, 4, my rise is 4. But instead of going up, I'm going down. So it's going to be negative 4. Okay, so because we read this from left to right, from this point to this point, it's left to right. So you have to go down. You can see the line is going down as well. So it's going to be a negative slope. So my rise is negative 4. My run is 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 squares. It's still positive, so my run will be positive 8. So negative 4 over positive 8 is negative 1 over 2 in lowest terms. So my slope is negative. So rate of change, just like our distance time graphs, the rate of change or the speed of a linear relation can be found using the slope or the rise over run, including units. It is the change in one quantity, dependent variable, relative to the change in another quantity, or independent variable. So here's an example. So the graph shows the volume of gasoline remaining in a car's tank. So here's the volume of gasoline on the y-axis, distance the car can travel on that gasoline on my x-axis, and I'm interested in calculating the slope of the graph. So the slope of my graph is a rise over run. So I take my 2 points, draw a triangle. Okay, and I'm interested in finding my rise. So my rise goes from 5 to 65. So this rise here is 60 units. And my run on my x-axis is 5 grid squares, but you can't just say 5. You have to look at the x value. So I go from 0 all the way to 500. So my run is going to be 500. Okay, so that means my slope is equal to the rise. And now my rise, look, be careful. Now you're going from left to right. So if you're going from left, my run is positive, but my rise is negative. It's going down. So it's negative 60 divided by positive 500. And in lowest terms, that is negative 3 over 25. Okay, and if I were to calculate this as a decimal, it would be 0.12. Now, what's this slope as a rate of change? Well, what's changing here? The dependent variable is changing, volume, liters, per independent variable, kilometers. So this car's tank is, this is negative 0.12. So this car's tank is losing 0.12 liters per kilometer. So this rate of change, I'm going to express this. This is basically it's just saying this is the slope, but tell me what the rate of change is. What is the units behind this? So using units. Okay, so I'm going to say here my conclusion is the volume of gasoline decreasing is 0.12 liters for every kilometer. I don't have to write the negative anymore because I'm saying in words it's decreasing. It's decreasing by 0.12 liters every single kilometer. And that's it for this video.